Hello everybody! I hope everyone's having a wonderful day. My name is Dr. Daniel Page. So today I'm going to be covering a couple of things, but before that I just want to let you know what you might need for this lesson. So the first thing is that you're going to need a stable internet connection, and otherwise you're also going to need a machine that you're going to need to install the software on that we're going to be using. Now if you already have Java installed, like all the files you're going to need that I'm going to talk about later, don't worry about the necessity of doing these steps. Just proceed on to the next lesson that we're going to do. So that being said, I'm going to address really the first question I have for you is what is programming? So I want to first talk about a more general concept, the concept of programming itself. It's used in various settings and more broadly captures the idea of planning tasks to solve some problem. So this problem might be achieving some objective. It might be providing a service. So just as an example, in my earlier life, I used to be a childcare worker. And in childcare, we do children's programming, where what we would do is we would lay out lessons and activities for the kids. And this would be done in a manner so that all the other workers in the area would understand what the schedule would be, the plan, the program, and also that it would be done in a nice, orderly or organized fashion. So that brings me to really talking about two real points here. Now, programming can be much more broader than this. For example, you may be familiar with television programming. A program can capture all sorts of things, ranging from a daily schedule to an objective for example, for a day, like a lesson plan. So some would call that a kind of programming. So these are broader notions of programming just to achieve some task, but they usually have two features to them often. Is that they're planned and organized in the sense that in advance you have some structure of tasks that you wish to complete, and they're normally ordered by which they need to be completed. So this is oftentimes given as a schedule, as in a list of tasks and when they have to occur, one after the other. So that's one aspect of this. And the other one is, the second one here is comprehensive. So if I give you a program, so a plan, the intention of the plan is to communicate the objective or way I could solve the problem. So if, for example, I'm doing children's programming, all the workers that look at my program need to be able to understand it. So the idea is very simple. If I give people that have my program, they should be able to actually read and understand it. So there will not be a confusion. Now, there's something about computer programming that's a little bit more narrow than just that it's comprehensive, that people can understand it. And that really brings me to the first thing I want to talk about when we talk about computer programming, is that it's a much stronger thing that we require here. In particular, we need this idea that it's not just comprehensive, it's that it's unambiguous. Unambiguous. So what does that mean? So it must be, so I mean it's exact and it generally has one interpretation. So normally in computer programming, it's only that there is one interpretation. So this is in contrast to ambiguous, where I can give you something, and it might be possible to interpret it in two or more possible ways, such that it either could contradict what it is, or it could be that it just doesn't mean what you intended to. It could mean a lot of things. The point is it's not clear. So it means unambiguous means clear. So we want to make sure when we do computer programming that our programs, our plans to solve some problem are clear. So I just want to give you an example of what I mean by this ambiguity and the way you can encounter it in normal daily life. So I want to tell you a funny story. So imagine you're going down the road. Imagine you're going down the road. And you see a sign see a sign on the road, and it says combat animal rescue. And maybe it says that below it says call now. And it gives some phone number. So imagine you see this sign on the side of the road, and it says combat animal rescue. And it says call now, and it gives some phone number. Now, if you've seen this sign and you didn't know that this was, for example, a business that does animal rescue, say it's a non-profit, for example. So there's a couple of ways you could potentially interpret this sign, right? I want you to think about it. So it says combat animal rescue. So there's one way I can interpret this, for example. It's that, okay, this is the name of the business, combat animal rescue. But there's another way you can also interpret this, is that it's combat animal rescue, meaning that I'm telling you to go after the animal rescue people and to call this number to do so. So is that really ideal? So you can call now to combat animal rescue. Is this clear way of advertising this business? No, it's ambiguous. Because if you've just seen this sign without any context, it's not very clear that it's really just the name of a business as opposed to telling you to combat animal rescue. Call now. So we want to avoid scenarios like this. And in computer programming, we cannot have scenarios like this when we write our computer programs. They have one exact meaning. So in computers, so in particular in computing more broadly, computations are determined in an exact mathematical, so mathematical meaning that dreaded M word, the thing that people fear sometimes. It's rather exciting when you talk about computing. And then there's this connection between what you want to calculate, which is a logical or mathematical kind of operation. So these are all exactly defined. So in computing, everything in terms of things is exactly defined. So for example, if I gave you the expression 2 plus 2. Now, if I asked you what's the result of 2 plus 2, now you would know that the answer is probably 4, right? Like this is equal to 4. But imagine if I gave you something that, like say if I gave you a computer, hypothetically, and it didn't know what addition was. You might have to define what this plus means. You might also have to define and tell me what a 2 means before I can add two things. In fact, you might also ask, how exactly do I evaluate this expression? These are the sorts of things that you would encounter if, for example, we did not know what that expression meant. But in computing, we work on fundamental operations like arithmetic. So these are things that are well defined, as in the sense that they're exact and they are clear. So this broader notion is really about unambiguity. I really want you to kind of hammer that idea. So this is the fun word of the day, is unambiguity. So just to summarize, and I want to, for dramatic purposes, read it from here, just so that way you know exactly what I mean. Digital computers are not humans. They lack agency and do as instructed. Computers do not understand in the sense humans understand natural language, as humans do. Digital computers process bits and bytes through computer hardware. So, like the machine I have over here. We'll see it in a moment. And it's worth noting that we're not going to really focus so much on the computer itself. We're going to be using it as a tool to perform computations. So these calculations that I'm talking about and the way we provide these tasks are going to be as instructions, and these instructions are going to be unambiguous. So I'm going to provide them to you in order, and the goal is to solve some problem. That's going to be generally the idea when we talk about computer programming. So generally, there's 4 things that computers tend to be able to do, and these are generally like the minimum requirements of a computer. Is that it processes. So for example, you may have a central processing unit, or CPU. It has the ability to store. So for example, this could be talking about your your hard drive, or persistent memory. So this is where you put your favorite cat pictures. And it may also have so-called active memory, such as random access memory, or RAM. So random access memory, for example, is where we often on a computer load our computer programs so that we can fetch instructions to process them one after the other. Just like if I gave you some plan, some program, it can go through each one sequentially. So classically, at least in that sense, that's how very often computers process things, one after the other. Historically speaking, computation has its roots in calculating things. So what do I mean by calculating? I'm talking about historically the idea of things like tabulating results of census, calculating the trajectory of stars or where stars are located in the sky, calculating sophisticated things such as ballistic missile trajectories. So that's like an example of a military application. That's something that would have been of much interest in the 20th century, for example. But the big thing I really want to hit home is that these are all mathematical calculations. So at the heart of computing is very much a specificity. It's a fun word. Specificity, meaning that it has to be specified, that it is done in an exact way, like I said. Now, I must stress that the earliest computers were us, humans. Very often, humans, with the aid of machines, such as basic tools for counting, like an abacus, or other types of tabulating machines over the years, helped gauge and evolve the concept of a computer. So, the concept of a computer in itself, like the stored program, digital computer of the 20th century, was a concept that evolved over a long period of time. The concept really came into being in the 20th century as a result of very interesting mathematics that sort of resulted in the foundations of computer science. But the big idea here is that we oftentimes would use machines to do these calculations sometimes, like calculating trajectories or figuring out where stars are in the sky. We'd use tools to do that, but these often had a single purpose. What makes a digital computer a little different from that is a big one, is that it's actually multi-purpose. It has programmable ability. So it has programmable ability. So what do I mean by that? That means you can actually feed the programs to a computer, and that could change the behavior of the calculations that the computer performs. So it's general purpose in that sense. So for example, a computer doesn't have to only add two numbers like 2 plus 2. It can actually do more sophisticated things like calculating trajectories and figuring out where stars are in the sky. But these are all things that are exact and clear in the way that they're formulated on the computer. So just to summarize everything. So when we talk about programming with a computer, when we specify operations and instructions we give the computer, just like if we were workers at some job, we have to actually be a little bit more narrow than that. We have to be that there is no ambiguity at all. It has to be clear. That's the big thing. So you can't just tell the computer, hey, make me some waffles. The computer may not necessarily understand how to do that. It may not even understand that you're talking to it. Remember, computers do not have agency. They do not have that ability. They just interpret and process instructions as you provide them to the machine. So now you might ask, Dan, why do you need this stuff to be all exact and clear like this and with no interpretation bias? Well, it's quite simple. Now, computers, they process bits and bytes. These are so-called machine code. So these are instructions that are written in a language that the computer's processor understands. It doesn't really understand it. It's fetched it and it performs the calculation. So normally, when we talk to each other about activities that we're going to do and solve, we need to think about it in terms of what exactly the computer needs to accomplish. Now, a computer, like I said, operates on bits and bytes. So how do we communicate with the computer? So that brings me to my friend over here. So this is my friend here.
This is my friend called Blotzo. So let me just get, I think I have a marker in my pocket. Okay, wait, it's in my hand. So Blotzo, are you there? Oh, there's Blotzo. Now, everybody say hello to Blotzo. So this is Blotzo the computer. Now remember, Blotzo is in fact a computer. It is not a human. So what I'm doing right now is I want to hypothetically imagine if Blotzo was an actual human being. So Blotzo right now is really happy. Now, if I was talking to Blotzo in the way I would talk to a human, if I asked Blotzo, hey Blotzo, add 2 plus 2 and return or output the result. Oh, it seems a little unsettling about that. Blotzo, what's 2 plus 2? Well, Blotzo, okay, Blotzo's telling me it's 4. So Blotzo says it's 4. See, that would be how I would communicate with somebody normally, but here's the reality, is Blotzo does not communicate like you or me. Blotzo operates on machine code. I want to just draw an analogy. Now, Blotzo, where's your lovely face? Okay, there's Blotzo's face. See, Blotzo is a little shy. See, Blotzo's a little shy. Okay. Hey, Blotzo. Blotzo. Okay. Blotzo is paying attention now. The big thing I want to get at is that Blotzo is a computer, it's not a person. So hypothetically speaking, imagine if Blotzo was a human. Now, imagine if Blotzo spoke in a different language than I do. And say it's a really complicated language for me to understand. Now, there's a couple of things I could do to communicate 2 plus 2s, and I wanted to return the result of 2 plus 2. What can I do for Blotzo? Well, the first thing is Blotzo speaks in another language. Now, I could be very compassionate and really take the sweet time to really want to wow Blotzo. Yeah, hey, look, I'm just trying to wow you, okay? Okay. Well, I could try to wow Blotzo by learning Blotzo's language and communicating in Blotzo's language 2 plus 2, like add 2 and 2, and return 4, or output 4. And if I were to do that, in the sense of that, Blotzo would indeed be able to tell me, okay, it's 4. So what exactly, so that's one scenario, right? But there's a problem with that. There could be many different kinds of instructions that Blotzo could compute. And I may not necessarily know how to speak every single one of those things, which takes a very long time. Computers are very sophisticated devices that actually operate on very elementary principles, such as processing bits and bytes. But those are added up over several layers of something called abstraction. So we have lower level stuff, such as the bits and bytes, but those represent things like numbers. And those numbers may represent portions of things like instructions that are read to the processor. Like I said, it can get rather complicated to go through each one of those one at a time. Now, another way I can do things is instead of trying to say, hey, Blotzo, and try to explain it in Blotzo's language and ask Blotzo to do it, I could instead hire somebody to be a translator for me. So imagine I want to make it so that I can return the result of 2 plus 2. What I could do is imagine I had somebody that could translate in Blotzo's language, the so-called machine code. What I could do is I could tell the translator, hey, add 2 and 2 and output the result of that calculation. And the interpreter can translate that and communicate to Blotzo. Then Blotzo can, of course, sit there and be like, okay, whatever, man, and return 4. So do you see how that actually can be a little bit more reliable, because the translator knows how to speak Blotzo's language and how to communicate in Blotzo's language. However, I don't really know it well. And Blotzo's language, now imagine if Blotzo's language could change per machine architecture. So for example, it could be a Windows machine, could be a Mac, could be a Linux. These all could be different types of things going on in between the operating system and the hardware. So that language could mean various different things. So when I talk about this problem, now Blotzo, I'm not trying to compliment you, okay? The point I'm getting at here is that Blotzo speaks a different language than you and me. Humans can oftentimes communicate instructions in mathematical terms like this, or logical operations. Blotzo operates on bits and bytes that are translated based on hardware and software specifications. So what we could do is we can make use of an interpreter, and that interpreter actually has an analog in computing. It's called a compiler. So here's the idea. The idea is very simple. My marker's here. So we have tools actually to take on the role of the interpreter. So if I want to get Blotzo to compute 2 plus 2 and output the result, I can use a compiler to translate some language that humans can easily understand, that follows some set of rules, into this machine code for some machine. In this case, Blotzo. So what exactly is that language that I'm talking about that I can give to the so-called translator, or now a compiler? That is a programming language. So what happens is I write my tasks out in a programming language. In this case, we're going to be talking about Java. And then I use a compiler to translate my code into that machine code. And that machine code can be executed by Blotzo. So just to summarize what I have said, so programming is the activity of writing computer programs. So just as a note, oftentimes when we talk about computer programs, we'll oftentimes say that, say if I write a program in a given programming language, I'll oftentimes refer to that as a computer program, even though I have to technically compile that programming code into machine code for the machine to actually calculate it. That would be technically the program. But we're talking about something that is technically equivalent in the sense that my programming language, in the sense that my code written up in a programming language, so these are my instructions one after the other, can be understood by Blotzo, but the code, so the machine code that Blotzo understands and the code that I wrote are technically and logically equivalent when Blotzo processes it. That's why we're going to refer to oftentimes when I write something, a program in, say, Java, I can call that a computer program, even though it doesn't really execute on the machine until I compile it. So hopefully that's clear. Anyways, Blotzo, that was really nice seeing you. So I'll see you later, Blotzo. Like I said, if we really wanted to, we could write all of our computer programs in pure machine code. However, that is not very helpful because, like I said, it's very expensive to do that. Now, that means that we can fall back on our idea of the programming language that can get compiled into a machine code that can be executed on some machine. We can fall back on that. And I want to stress that there isn't just one programming language. There's large families of programming languages. That the whole idea here is that you have a program that you write in a programming language, and then you compile it, and you get some machine code. And this runs on the machine. I'm going to be kind of vague on what machine means. In some programming languages, it actually literally means your computer directly. So for example, in C++, you'll get an executable that runs directly on the platform that you compile it on, like Windows. So that brings me to one point I really want to talk about. It's really the process of programming, and I want to hit on a few points. So the first thing I really want to think about is that you can have an idea. So when you think about, you want to say, I want to use computer programming. First, think about if you have an idea of what you would like to implement on a computer using programming. So first, make sure that you can see if you can exactly specify it. Remember, we want to have things that are unambiguous if possible. But the big question I really want you to think about, and I'll let you really think about this, is does it make sense to use a computer? So once you have some idea, I want you to think about it and maybe try writing it down. So you might write down, for example, what you would like to complete. So these could be a bunch of tasks. Like I said, when you write out a computer program, you're going to order tasks one after the other as instructions to perform calculations. And these calculations may be to achieve some goal. For example, calculating 2 plus 2 and see what the result is. So I usually advise to write it down. Sometimes things you have as an idea in your head don't make a whole lot of sense until you write them down. So pick out a pencil and paper or pen and paper and really just try writing it down and see if it makes sense. This might be more formal work, for example. If you're doing some sophisticated mathematical, the dreaded M word, sophisticated mathematical calculation, it may be the case that maybe you have to be very careful what you're calculating. Maybe it might be incorrect if you don't do it correctly. A lot of work in computer science happens at this stage. So for example, it could be like a researcher like me that studies algorithms, and I spend almost all my time looking at more of this side. Not so much talking about actual programs, because it's really about solving problems, and that's fundamentally a mathematical pursuit when you talk about computation. So that's just an example. Now, once you're satisfied that it's clear enough, by the way, I usually recommend trying to do this as a beginner programmer, because very often students are very easy to jump right onto the computer and just say, I'm going to just try whatever. Sometimes it works for some people, sometimes it does not work very well. I usually recommend if you have an idea, try brainstorming it out on paper, and then see if you can see a nice organized way of writing it down, instruction after instruction. Like I said, I haven't gone into too many details what these instructions would look like. We'll see that in future videos here, or future lessons. So once it's clear enough, what you're going to do is you can write a computer program. So imagine these are all your notes. What I would like to do is I would like to input those into my computer. Look, this is a lovely picture of a laptop. Isn't it beautiful? And I would enter in each one of my tasks. So instructions, remember, all of them have to be clear, right? They're going to be things that you're going to translate into that programming language. Sometimes things do not translate very easily into a programming language, so you have to keep that in mind when you're planning things out. So you can, of course, you'd write a computer program. So this would be in the programming language of your choice. So it could be something anywhere along here. So you write in a computer program. And now the big thing, and like I said, like the translator I talked about earlier, you're going to have a compiler. So using a compiler for that given programming language, you would compile this into a proper computer program. For a machine to execute. So this should just be a bunch of zeros and ones. I don't know what these mean. I just sort of threw these off the top of my head. So the point is that it takes your code that you wrote. Remember, programming languages are designed for humans. They're not for computers, really. The idea here is that it's something that you can write the instructions for so that you can turn it into machine code for the computer to process it. So this is the general gist. Now, in the future, beyond this, you might revisit your computer code here, your code. So this would be your code you're writing up over here. So you might revisit your code and you may want to add more features or may revise some parts of your program so that you can enhance the features of your program. So this is not really the end of the story sometimes when you're developing software. Sometimes it keeps going. Now, there's just a few things I want you to be aware of when we talk about the Java programming language. So let me talk a bit about that. In Java, we have several different components I want you to be aware of. And these are going to matter when we start talking about installing software in a moment. So when we write code in Java, we write Java source code. So the files that these are usually use the extension name Java. So for example, if I have a file called my Java file, at the end of the file, you'll see .java. So that's how you know it's actually a computer program in the given programming language. So this would be, for example, my instructions that I typed out in Java, so the programming language Java. Now, it's worth noting that when you compile Java code like this, you end up with something called Java bytecode. So Java bytecode is the so you can think of this as your compiled code. And I'm going to talk about one moment what makes this a little unique compared to the scenario I brought up earlier. So these are .class files, so the extension is class. So for example, it would be my Java file .class. You'll see why we would call it class like this in a future video or lesson. So in a future lesson, we'll see what I mean by why it should be class like that. And these guys right here, these bytecode, so this is our compiled code from here, and it's for something very specific. So I talked about a machine. Now in Java, we have something called the Java virtual machine. So this is often referred to as the JVM. This is a part of something called the Java runtime environment. So it's part of the Java runtime environment, or JRE. And this is what's going to happen. I'm going to show you the process for which you go from a source code. So similar to my picture I had before, once I have a program, how you get from a program to something that got executed on your machine. So if I was using Windows, I would start off with my Java source code. I would use the compiler called JavaC. And don't worry too much about the details about that. I have some details in the notes towards the end of this section about that. And you get Java bytecode. So this can be thought as the machine code for the JVM. And what the JVM does is for your platform, so say for example I have a JVM for Windows, what it does is it will translate these Java bytecode instructions into the machine code of my computer. So it's a program that's going to translate my bytecode into code that's going to be executed on the machine. So it's a program that translates my code into the machine code. So it's kind of meta like that. It's kind of interesting. Now, the big perk about this is notice that if I have Java bytecode, I can have multiple different kinds of Java virtual machines. One maybe for each one of the major operating systems. Like say I can have a Mac. Maybe I can have Linux, for example. The point being is each one of these can have its own JVM. So you can have a Windows machine, you could have a Mac machine, you can have a Linux machine. And each one will produce machine code that gets run on your on the computer. So this is something we would call, if you want to get very buzzwordy, it's a word I made up, I think. It could be a word tomorrow, I don't know. It's platform independent. So as long as you have a JVM, and that JVM indeed works the exact way you would expect it to across all these platforms, it doesn't matter. You have bytecode, and it could be interpreted by that JVM for your machine. So just to plain language, you have code, it gets compiled into bytecode. And if you have a JRE, it has a JVM. And this JVM does the job of translating your Java bytecode into machine code for your machine. So that brings me to another point here. So it's worth noting that as long as we have the ability to type in a manner of the programming language, it doesn't really matter which tools we use, as long as we can input it as given in the programming language. We follow its rules. So it's going to be very much like we're learning a language. So when I talk about that, you really could just sit around using a text editor for everything we're going to do here, at least when it comes to the programming aspects of this series, or all the lessons we're doing here. However, I'm going to use something called an integrated development environment. So-called it's an IDE. So what is an IDE? It's software or program that provides tools or facilities for computer programming. So common features of an IDE tend to include the following. It doesn't have to just be these. I just want to point this out. So oftentimes, well, most of the time, you're going to encounter that has a code editor, because obviously you want to have the ability to type in the code so that you can write out your computer program in, say, for example, Java. So you want to make sure you have some code editor. So code editors oftentimes have different features like code completion. So for example, if you start typing in a key phrase or keyword that's been used before, it'll try to give you a pull down or autofill menu and allow you to select something you've already defined previously. Another thing is syntax coloring. So for example, in Java, like other programming languages, there are very specific rules you have to follow. It's like learning another language. So oftentimes IDEs will color certain parts of text or keywords, or even change the fonts of them to make it easier to see what things are your code or other things are key structures of the program. So these are a couple of features I wanted to point out. Refactoring is another thing worth noting. So some IDEs have refactoring tools. So what's refactoring? So just in plain terms, because we're not going to talk too much about these things in this series, refactoring is, imagine you write out a whole bunch of code and you find yourself saying, hey, look, is there any way I can write less? I can simplify all of my code a little bit further. So for example, you might write out a lot of redundant stuff. And that often happens when you have big, complicated pieces of software. There might be actually a nice, more cleaner way of organizing all your code. So refactoring is an activity that programmers and developers get into quite often. It's a very regular activity, but sometimes IDEs have the features to really help you simplify down some of these core instructions that your program may have. Another very important one is, of course, compilation or build automation tools. So what do I mean by this? Remember, I told you that we have to take the program we've written in Java, for example, and compile it into Java bytecode. So it'd be nice if our IDE was able to compile the code for us by just pressing, like, say, a little button or something, like a little green go button or something. Something very easy to do, or some keystroke on your keyboard. So these are features that as software does get more complicated, you oftentimes have to worry about packaging files in a very specific way to compile and build your software. So sometimes IDEs will have ways to help you do that. Another really valuable tool is a so-called debugger. So what exactly is a debugger? Well, oftentimes when we write out instructions for a computer program, it's sometimes possible to create logical errors. So things, for example, if I was trying to add 2 plus 2, instead if I went 2 minus 2, for example, my intention was to add 2 plus 2. I want to have 2 plus 2. That would, for example, be a logical error. And this is an example of something called a bug. You can think of it as error, and it's usually a logic error. So some problem that is unanticipated about your program. So some mistake that you made while you're writing the program. So a debugger, as the name suggests, it's a tool to help you eliminate bugs from your code. Bugs persist in very complicated pieces of code all the time. So oftentimes debuggers are a nice tool to help you identify if you see some unexpected behavior coming from the output of your program. So for example, there's often, that being said, you need to think about what tool works best for you. So for example, we're going to be using the Eclipse IDE. So we're going to use Eclipse. I'm not obviously going to require anything of that sort. You could just use a text editor as far as I'm concerned. But the point is that I'm going to pick Eclipse, but you don't have to use Eclipse. I'm going to show you how you can install Eclipse. And we're going to see that in a moment here. So just be aware that not every IDE is the same. Some have different features than other ones. And sometimes you don't necessarily need all this suite of features. If you're writing a very simple program, you don't need all these crazy features sometimes. Some of these get really complicated sometimes. So that being said, I want to move to the next part of our lesson, where I need to show you how you get the software. Okay, let's, beautiful, beautiful. So anyways, the first thing we're going to do is I need to mention a couple of things. So first, you're going to need this so-called Java Development Kit. So it's called the JDK. So the JDK contains both all of the stuff you're going to need for developing. So these are just a suite of programs for compiling your Java program. So for example, Java C. This will contain all of those programs. And it also will include the JRE. So I mentioned the JRE earlier. That contains the JVM. So both of these things are going to be contained in this so-called JDK. And how we're going to get the JDK? Well, we're going to follow. So I'll have the links of all these things in the description. But you're going to go oracle.com and you're going to go find Java SE downloads. And you're going to locate a version that is appropriate for you. I'm going to be using a 64-bit system. So if you're not really sure what architecture your computer uses, usually you'll find out quite quickly if you download the file and it'll tell you, oh, sorry, this isn't compatible with your system. You may have a 32-bit system if your computer is very old. Like, I mean very old, I mean well over a good decade or so. Unless you're using a very rinky-dink computer. No offense. So anyways, with that being said, you'll find that there's a variety of versions here. If you need, say, for example, a 32-bit system, so for example, if you're using an older Windows system, you may consider using Java SE 8. So the 8 version here, if you just go to JDK download, you can follow through the similar steps. You may have to make an account here. This is the so-called Oracle JDK. There's different JDKs out there on the internet. Some are open source. This is one of the official ones. So I'm going to go to JDK download. And just take a look at the licenses, just in case you really just want to get into the nitty-gritty. Sometimes these licenses have certain permissions on them. This one, I'm not aware. What you do is you find the operating system that you're using along with the platform you're looking for. So I have a 64-bit Windows system, so I'm using Windows 10. I would select this one. Note that the page may look different in the future, but the point is the general gist of the instructions. So I'll just click on this. I'll get a downloader, and I would get an installer. So let me pull up the installer of the files. The reason why I mentioned you need a stable internet connection is because very often you'll have it where like these files can be kind of big. So what you do is you'd walk through this. I recommend using the default directories that they provide unless you really need them to be a little different. So I'll just go next. And it will perform the installation. So you normally just sit here for a good while. So next I'm going to show you how you get Eclipse. So you're going to go to eclipse.org and you're going to go to downloads like I have up here. It'll usually recommend you the most recent version. So for example, I have this version here. I would just go download and it would recommend a server to download it from. You can pick one if you like. You just click on download and it will allow you to select the file. This will be the installer. And you'd want to download that. So it's pretty straightforward. But so once you have that, you'll open up an installer, and the installer will pull up to this. The thing I want you to be aware of is that we're using Java here. So there's a whole bunch of different versions of the Eclipse IDE. What you're going to use is the one at near the top. It might be a little different in the future, but you're going to go Eclipse IDE for Java developers because we're implementing things in Java. So you click there. I recommend making sure that these directories exist. So this brings me to a very important point. You need to install the JDK before you install Eclipse. So do not skip the first step if you do not have the Java JDK. Otherwise, these directories will not exist. So what will happen is you'll make sure that these match up with the folders in your file system for where the JDK is located. I recommend looking in and making sure that these files indeed exist. But yeah, I have this version of the JDK. By the way, it doesn't really matter too much which version of the JDK you're using. As long as it's 8 or up, everything I'm going to show you works. So you just click install and you'd walk through the process. Really straightforward, right? So anyways, that's really just those are the 2 steps I really just needed to do with you guys. So let me get back up here. Anyways, today we've seen a bunch of different concepts. We've seen what programming is a little bit. We talked a little bit about how that whole process of starting at an idea all the way to a computer program to something that actually executes on a machine. We talked a little bit about how Java works. And we also talked about how we can get, say, the JDK and Eclipse on your computer so that we can start doing our fun programming activities. So next time we'll see how we can write our first Java program. So I'll say thank you very much and have yourself a beautiful day. I'll see you later.